Okay, so in this small tutorial, we want to learn about the expression for the period. Did I have an expression of period? I forgot, right? Period. Did I have an expression of a period of a physical pendulum, which is a rod of a mass m, length r, and moment of inertia 112 mr squared. This is the given thing you have, and now use this physical pendulum as a rod to find out its period. Right, so we have to use our calculus, we have to use our torque equations to derive this period. Okay, so first let's draw the rod. Let's say the rod has a length r. Okay, so let's see if this is a rod which has a length r, right, from here to all the way here is a length r. From here to here is a length r. And now if suppose you have the rotational point or rotational axis from right there, if you are rotating from that point, you have the distance from that rotational axis to the center of mass, which is right there. Okay, so that must be the r/2 distance from the center of mass to the rotational axis. Of course, its weight or mass times gravity is pointing downward, and you are going to be rotating. So from a center of mass, you will be rotating, back and forth, back and forth. Hence, you are going to have a small angle right here about which you are going to be rotating. So if that's the case, as always, this is going to be your mg sine theta, which is responsible for the rotational of this rod, mg sine theta. Okay, so you had the rod in equilibrium position, and then you move the angle theta and then let it go, and that's how it's going to rotate. So this is not a simple pendulum because you have a rod which has an extended mass, right? So it's not considered as a simple pendulum at all, right? So we have to do what? We have to do first calculate the rotational inertia. So we can write the first calculate the rotational inertia, calculate the I, okay, about a rotational axis which is right there. Okay, so we can say the rotational inertia I is ICOM, center of mass, plus mr square. Okay, plus mr square. So what we can do here is when you have this simple pendulum, you need to make sure that actually this is the distance r/2, by the way, right? Because you're moving only from there to here, which is r/2. Okay, so we can put down ICOM, which is given to you, which is 1/12 of mr square. You know that this is mr square over 4. Okay, and when you do the math out, this comes out to be as a 1/3 mr squared. So this is your new I for the rod about which it's gonna rotating. So the restoring force, again, as you said, mg sine theta, we're gonna have it, which acts at the center of mass of the rod and which will provide the torque. So we can write something here about a restoring force. Okay, we have mg sine theta, which is acts at a center of mass, okay, of the rod, center of mass of the rod, and which provides the torque, which provides the torque, right? So torque tau, you can write torque tau is equals to r/2, which is the perpendicular distance to the mg sine theta, and that is the torque. Now, of course, there is the only one torque because there is no hinge providing any sort of torque, no friction, no other thing. So torque tau equals to I alpha, and instead of that, you can have a negative r2 mg sine theta equals to 1/3 of mr square. Alpha you can write that way. As you can see that your sine theta is equals to your close small angle approximation becomes theta, and hence you can write that mm cancels out, some r cancels out, right? So you will eventually have your alpha exactly as negative 3g over 2r sine theta. Of course, we said small angle approximation, so we'll change it to 3g over 2r theta, right? That's the alpha. And as we know, alpha is nothing but d squared theta over dt squared. That is exactly equals to negative 3g 2r theta. This is now comparing, right? If we compare with the simple harmonic motion of a rigid body right here, you can have a d square theta dt square. Remember the omega square theta? So you can compare your omega with negative 3g over 2r. Now here's the secret. Every time, it doesn't matter what shape you have, you will derive the equation like this. First for moment of inertia, then for the torque, then for the alpha, and then boom, you're going to compare that with the existing d squared x dt square or d squared theta over dt square with the omega. And then omega will give you the period time t. Okay? So here, one more time, your omega right here, which is comparing 3g over 2r. So we can say omega square is nothing but 3g over 2r, which is equals to omega, which is equals to square root of a 3g over 2r. That is nothing but 2 pi over t. Hence, your t equals to 2 pi square root 2r over 3g. As you can see that in all of this simple pendulum or torsion pendulum or a physical pendulum, in case of a rod, the object has a different constant in front of a g, right? This is 2/3 of a g, right? But in all cases, the period is mass independent. It does never rely on the pendulum's mass, right? So simple pendulum or a torsion pendulum or a physical pendulum of a shape rod with the mass m, it's not depending on its mass, right? So this is it. That's the period for the physical pendulum. In this case, it's the shape of a rod. Thank you. I hope this helped.